Okay, this is my first attempt at a video. Last time when we met in class, I think we were working on chapter 9. I think we covered 9.1, 9.2, 9.3, and part or all of 9.4. By the way, continue to study the textbook and do homework problems from the textbook or ebook. Also continue to do problems, your homework problems from MyMathLab. Watch the videos there. Look at the examples in MyMathLab to help you understand the material. So since I think we've gone over 9.1, 9.2, 9.3, and all or part of 9.4, I think I'll start with 9.4. 9.4 is simplifying radical expressions using properties of radicals. So last time I gave you the definition of a radical in simplest form. Here it is again. A radical, the nth root of a, is in simplest form if no perfect nth power is a factor of the radicand, there are no fractions in the radicand, and 3, there are no radicals in the denominator. Here are a couple rules we use to help us simplify radicals. The product rule: the nth root of a product is a product of the nth roots, so the nth root of a times b equals the nth root of a times the nth root of b, long as everything's defined. You don't have like a square root of a negative number or something. And the quotient rule is the nth root of a quotient is the quotient of the nth roots. The nth root of a over b equals the nth root of a over the nth root of b. Again, everything has to be defined. You know, b can't be 0. You can't take the square root of a negative number. Those kinds of things. Okay. I think we did a bunch of problems in this section, but I also showed you what we looked at perfect squares for numbers already. Here are some squares involving variables. X to the first power is x squared squared is x to the fourth, x cubed squared is x to the sixth, etc. These are squares of variables to integer powers. Notice all the exponents are even. So when you square something, the exponent is divisible by 2. When you take the square root, then you undo that squaring or the doubling of the square root. So the square root of x to the 10th is x to the 5th. Why? Because x to the 5th squared is x to the 10th. Recall that the square root of x can be written as an exponent. So the square root of x to the 10th, for example, would be x to the 10th to the 1/2 power. And by properties of exponents, we multiply those exponents together. 1/2 of 10 is 5. So taking a square root is really, it just boils down to multiplying the exponent by 1/2. Here are some cubes involving variables. X to the first power cubed is x cubed. X squared cubed is x to the 6th, etc. Look at all the exponents. They're multiples of 3. 3, 6, 9. So when you cube something, you triple the exponent. So when you take the cube root, you divide the exponent by 3. For example, since x to the 4th cubed is x to the 12th, the cube root of x to the 12th is x to the 4th. If we wrote it in exponential form, the cube root of x to the 12th is x to the 12th to the 1/3 power. Using properties of exponents again, we multiply the 12 and the 1/3, and we end up with x to the 4th with an exponent of 4. Similarly, for 4th powers, notice the exponents are divisible by 4. They're multiples of 4. 4, 8, 12, etc. Those are perfect 4th powers. 5th powers involving variables, notice x to the first power to the 5th is 5, has an exponent of 5, x squared to the 5th. You multiply the exponents, you get x to the 10th. So the exponents are multiples of 5. They're divisible by 5. So the 4th root of x to the 12th, for example, would be x cubed, because x cubed to the 4th power is 12. If we wrote it in using the radical and exponential form, we could say the 4th root of x to the 12th is x to the 12th to the 1/4. Multiplying the exponents, 12 times 1/4 is 3, so we get x cubed. Similarly with a fifth root, the fifth root of x to the 20th, it's x to the 4th because x to the 4th to the 5th power is x to the 20th. And the fifth root undoes the 5th power, or writing it with an exponent, the fifth root of x to the 20th is x to the 20th to the 1/5 power, multiplying the exponents again gives us x to the 4th. So let me do some of the examples out of the book. This is on page 634, example 1. Directions are to multiply. I might also say simplify. The square root of 5 times the square root of 3. Using the properties of exponents. This one, the product rule, we can either change the left side into the right side or the right side into the left side. If we have two radicals multiplied together, we want to write it as one radical. So since they're both square roots, notice if the nth root of a times the nth root of b is the nth root of a times b. As long as the indices are the same, both the same root, we can multiply the radicands together. So this becomes the square root of 5 times 3, which is the square root of 15, which can't be simplified because there's no perfect square that divides 15. Another example is, suppose we had the cube root of, let's say, 2 times the cube root of 5. Notice the indices are the same, so we can write it as one big cube root and multiply the 2 and the 5 together and get the cube root of 10. And this can't be simplified as we discussed in our last class, but I'll go back over that in a minute. But those are some examples. If there's variables involved, that's fine. Say we had the fifth root of 3x squared times the fifth root of 4x. They're both fifth roots. The indices are the same. Therefore, we can write it as one big fifth root, multiply 3x squared times 4x, all underneath the radical symbol. And we end up with the fifth root of 3 times 4 is 12. X squared times x is x cubed. The fifth root of 12x cubed. So those are some examples. Those are examples like example 1, and as I said, on page 634. The next section discusses how to use the product property to simplify a radical. Again, this is the product property. Now, we did this in class, but I'm going to go back over it a little bit. So, say we're supposed to simplify the square root of 50. Now, this is a square root. That means the index is 2. We don't need to write it, but the index is 2. We usually just write it like this. So we're looking for any perfect squares that divide 50. Perfect squares are 0 squared, which is 0. 1 squared is 1. We don't care about those, but 2 squared is 4. Oops. 3 squared is 9. 4 squared is 16. 5 squared is 25, etc. If any of those perfect squares divide 50 evenly, we can use the product rule for radicals to simplify it. So what we want to do when we have a problem like this, we want to factor the radicand, a times b, so that either a or b is the largest perfect square that divides this a times b, whatever that product was. Then we can simplify the radical. So we're looking for the largest perfect square that divides 50. 25 is the largest perfect square that divides 50, so we'll write 50 as 25 times 2. Then using that product rule, we can write it as the square root of 25 times the square root of 2, and the square root of 25 is 5. So we can replace the square root of 25 with 5 and write it as 5 times the square root of 2. 2 is a prime number. There's no perfect square that divides that. There it is in simplest form. Another example, let's try a cube root. Let's say the cube root of 54. So the cube root of 54, now we want to find the largest perfect cube. Notice the index is 3. So we want the largest perfect cube that would divide 54. Perfect cubes, 0 cubed is 0, 1 cubed is 1. Again, we're not worried about those, but 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, etc. Notice 27 is a factor of 54. So we'll write the 54 in factored form as the perfect cube 27 times 2. Then we can write this as using the product rule property. We can write it as the cube root of 27 times the cube root of 2. The cube root of 27, since 27 is 3 cubed, the cube root of 27 is 3. So we can write it as a 3 times the cube root of 2. Notice I didn't write the cube root over the 3. I took the cube root and wrote it as 3. No radical once you simplify it. And 2 is prime again. There's no perfect cube that divides 2, so there it is in simplest form. Notice you can't just factor 54 any way you want. 54 is 6 times 9, but that doesn't help me. I can write it as a cube root of 6 times the cube root of 9, but 6 and 9 are not perfect cubes, so I can't simplify either one of these, so it doesn't help me to write it this way. It's correct, these are equal, but it doesn't help me write it in simplest form. I want to do it like this. You could also factor 54 completely, so you could, let's say you wrote it as 6 times 9, then you kept factoring. You say, oh, 6 is 2 times 3. 9 is 3 squared. So we can write this as the cube root of 3 times 3 squared, which is 3 cubed, times 2. Remember, anything with an exponent of 3 is a perfect cube. Taking a cube root is dividing 3 into the exponent. Since that exponent there is divisible by 3, I can just say 3 goes into 3 one time. I've taken the cube root now. It's 3 to the first power. I don't have to write the 1 times the cube root of 2. Now, we did these in class, so you should remember that. But that's another way sort of looking at that one. If some variables involved, we're going to do the same kind of thing. For example, let's say we wanted to find the square root of, let's say, how about 32x to the 5th power times y times z to the 10th power. And we did some of these types of problems in class, so you should recall. Okay, I'm going to use the product rule again by factoring this, the radicand, into a perfect square times something that has no perfect square as a factor. So let's do that. So we have square root of, let's find the largest perfect square that divides 32 is 16. Notice 16 is a perfect square. On the other hand, we could write 32 as 2 to the 5th. You can do it like that too. I'll show you that in a minute, but we could write it that way. But let's just realize that 16 is the largest perfect square that divides 32, and write the 32 as 16, the largest perfect square that divides 32, times 2. X to the 5th has a perfect square in it. Remember, a moment ago I showed you this, what variables look like if they're perfect squares. They have even exponents. So we want the largest one that divides x to the 5th. And as I showed you in class, you want to pick the exponent to be the largest even number that's less than or equal to 5. Since 5 is odd, it's not a perfect square, but x to the fourth is, and x to the fifth can be written as x to the fourth times x to the first power. Notice this exponent here, the exponents over here are 1. They're less than the index. There's no perfect square in there. Y has an exponent of 1. In order to have a perfect square that divides this, it's a factor of this, the exponent must be at least what the index is. The index is 2 here. Since the exponent is less than 2, this stays underneath the radical symbol. I can't simplify it. So I'll put it over here with the non-perfect square part. Z to the 10th, the exponent is 10. That's an even number. That means that's a perfect square. So let's write the z to the 10th over here in the perfect square part. So this 16x to the 4th z to the 10th is a perfect square. The other factor, 2xy, where the exponents are all less than the index, notice, is not a perfect square. Now we use the product rule, and we'll write it as the square root of 16 times x to the 4th times z to the 10th times the square root of 2xy. This first factor, this first radical, can be written without a radical symbol because the radicand's a perfect square. The square root of 2xy is going to stay the way it is. So the square root of this one, the square root of 16 is 4. Let's see if I can squeeze it in over here. Let's see. So it's 4. The square root of x to the 4th, remember, taking a square root is really multiplying the exponent by one half, or taking half the exponent. So the square root of x to the 4th is x squared. The square root of the z to the 10th is z to the 5th. No radical symbol. That's the square root of this part. Then this other factor with the radical stays the way it is. You can't simplify it because 2 has no perfect square and that divides it. It's prime. The same is true with x and y. There are no perfect squares that divide those. So it stays underneath the radical symbol, and there is that one written in simplest form. Here's another one. By the way, you can stop the video when I start a problem, after I write it down, and you try it, and then turn the video back on and watch how I do it. Another example, let's say we have 20, the square root of 24. Or let's do, let's do a cube root this time. Let's say the cube root of, let's make it 48. Cube root of 48. Let's say x to the 30th power times y squared times z to the, let's say, 29th power. And you want to simplify that one. Okay, so we're taking a cube root, so we want to factor the radicand if possible. And by the way, notice when we did these problems up here, see the square root of 15, you're done. When you multiply the square root of 5 times square root of 3, square root of 15, you're done. There's no perfect square that divides 15. Same thing with this product of these cube roots here. The cube root of 2 times the cube root of 5 turned out to be the cube root of 10. You're done. You can't simplify that because 10 has no perfect cube that divides it. The same thing with this third example. There's no perfect fifth power divides 12x cubed, so you're done. It's simplified. Okay, back to this problem. If there's any perfect cube that divides the radicand, we can simplify this one. 48. Let's see, perfect cubes. 8, 27, 64. Oh, 48 is 8 times 6. So we're going to write the radicand, the 48, I'm going to write as 8, a perfect cube, times 6. X to the 30th. Now remember, perfect cubes, here they are here, have exponents that are divisible by 3 or multiples of 3. That's what 30 is divisible by 3. So x to the 30th is a perfect cube, and when I take the cube root of that, I don't need to have a radical symbol. I'm going to just divide 3 into the exponent and write x to the 10th. Y squared. In order for this to have a perfect cube in it, the exponent, when you have variables, must be greater than or equal to the index. It has to be 3 or greater. It's not. Y squared has no perfect cube in it, so I'm going to put it over here in the factor that is the non-perfect cube part. Z to the 29th. The exponent is 3 or bigger. There's a perfect cube in there. Perfect cubes have exponents that are divisible by 3 or multiples of 3. So I'm going to find the largest number that's less than or equal to 29 that is divisible by 3. That's 27. So I'm going to write the z to the 29th as z to the 27th times, it still has to be equal to z to the 29th, so I need a z squared over here. Since z to the 27th times z squared is z to the 29th, you add the exponents. Now I've written it as a product. The radicand is a product where one of the factors, this one, is a perfect cube and this one's not. So now I'll use the product property, and write it as the product of two cube roots, the cube root of 8x to the 30th times z to the 27th times the cube root of the other factor of the radicand, 6y squared z squared. This part is staying the way it is. You're not going to write it without a radical symbol. That first part, that first factor, you're going to rewrite this one because you're going to take the cube root of this radicand because the radicand is a perfect cube. The cube root of 8 is 2. So it is 2. The cube root of x to the 30th, divide 3 into the exponent. Remember, cube root means 1/3 power. So you'd raise x to the 30th to the 1/3 power, and you'd end up multiplying 30 times 1/3, or divide 3 into 30. So x to the 10th is the cube root of x to the 30th. And in a similar fashion, the cube root of z to the 27th, all I do is divide 3 into 27, really, and that's z to the 9th. That's my exponent 9. Times, don't forget to write the little index here, the cube root of 6y squared z squared, and I'm done. Okay. Just a comment here. I could have written 48 as a prime factorization and done it just like I did, do that part just like I do the part with the variables. 68 is 6 times 8. But if I factored it completely, it would look like this. See, 48 is, let's write it as 8 times 6. That's 2 cubed times 2 times 6, or 3, 2 times 3. That would be 2 to the 4th power times 3. That's another way of writing 48. So if I was doing this problem, I could say it's a cube root of, factoring 48, I would get 2 to the 4th times 3 times x to the 30th times y squared times z to the 29th. Now, just like we did before, I'll factor this into two factors, one being a perfect cube. So we'll write this as a big cube root here. I want the largest perfect cube that divides 2 to the 4th. Just like when we work with the variables, like x to the 30th is a perfect cube because the exponent is divisible by 3. Z to the 29th has a perfect cube in it because the exponent is bigger than or equal to 3, and it has a perfect cube in there. Y squared did not have a perfect cube because the exponent wasn't greater than or equal to the index. But notice 2 to the 4th, the exponent is greater than or equal to 3. So I'm going to write the 2 to the 4th as 2 to the 3rd. I'm going to use it. I want the exponent that's as large as possible, that's a multiple of 3. That would be 3. So I'm going to write 2 to the 4th as 2 to the 3rd times 2 to the 1st power. 3 to the 1st power, the exponent is 1. That's less than 3. There's no perfect cube in there, so I'd write that as over here in the non-perfect cube part. And then the variable part, I do just like we did before. Rewrite it like this. See, x to the 30th is a perfect cube. The z, or the y squared, went over here because the exponent was 2, which is less than the index, so no perfect cube in there. And then the z to the 29th, we had written it as z to the 27th times z squared over here. It's hard to see, but okay. Then, just like we did before, we use the property, the product rule, and we write it as the cube root of 2 cubed, x to the 30th, z to the 27th. That radicand is the perfect cube part over here, times the cube root of the radicand. 2 times 3. Notice the exponents are 1, so there's no perfect cube in there. We might as well multiply it out. We should multiply it out and write it as 6 times y squared times z squared, just like before. Then this part, the cube root of 2 cubed, 3 goes into the exponent, 3 one time, so that's 2 to the first power when you take the cube root, which is this, just like we got before. And then you take the cube root of x to the 30th and z to the 27th, and you get x to the 10th, z to the 9th, just like before, and you get the same answer. Okay? But anyway, that's a review of some of the kind of problems we've done. Let's do a fifth root, just for the heck of it, just to take a look at that. Let's say I asked you to simplify the fifth root of 16. Let's use some other letters here, also some more letters. Let's say w to the 4th times x to the 40th, y to the 28th, and times z to the 9th, let's say. And again, if you want, stop the video, try to do it, and then start it back up and watch as I do it. Okay. I want the largest perfect fifth power that divides the radicand. 16. 16 in factored form, here, let me just factor it here. 16 is 4 times 4, or 2 to the 4th. There's no perfect fifth power that divides 16. In fact, if we looked at fifth powers, we don't care about 0 to the 5th, which is 0, or 1 to the 5th, which is 1, but 2 to the 5th is 32. 2 to the 5th, no, 2 to the 5th is 32. So the largest, or the smallest perfect fifth power that's an integer is 32. That's positive is 32. 16 smaller than that. So I'm going to leave the 16 underneath the radical symbol. If you want to write it as 2 to the 4th, that's fine. So you can see that there's no perfect fifth power in there, but that stays underneath the radical. So that is not, there's no perfect fifth power in there. So I'm going to put it over here with the non-perfect fifth power part. W to the 4th. Notice the exponent's 4, which is less than the index. So I'm going to put w to the 4th over here with the non-perfect fifth power part. X to the 40th, though, 40 is bigger than or equal to 5. So there's a perfect fifth power in there. Remember, perfect fifth powers have exponents that are multiples of 5, divisible by 5. 40 is such an exponent. 40 is 5 times 8. So x to the 40th is a perfect fifth power. So I'll put it over here in the perfect fifth power part. Y to the 28th. 28 is an exponent bigger than or equal to 5. There's a perfect fifth power in there. Y to the 28th is not a perfect fifth power. It is a factor that's a perfect fifth power, but not y to the 28th, because 28 is not a multiple of 5. 5 does not divide 28. So I want the largest exponent that's less than or equal to 28 that's divisible by 5. That's y to the, I use an exponent of 25. That's the largest perfect fifth power that divides y to the 28th. Now I still have to have y to the 28th underneath the radical symbol, so I need a y cubed over here, so I still have the same problem. See, y to the 28th times y cubed, add the exponents, we get y to the 28th. Z to the 9th. An exponent of 9, 9 is greater than or equal to 5. So again, there's a perfect fifth power in there. I'm picking the largest number that's a multiple of 5 that's less than or equal to 9. That would be 5. So I'm going to write z to the 9th as z with an exponent of 5, perfect fifth power here, times z to the 4th. So I still have z to the 9th underneath the radical. Now this first factor I'm putting in a grouping symbol here, that's a perfect fifth power. The second factor in that parentheses is not. It's going to stay underneath the radical symbol. So let's use properties of exponents again and write it as a product of 2 fifth roots. This is the fifth root of x to the 40th times y to the 25th times z to the 5th times a fifth root. Don't forget to write those little indices there, of 16 w to the 4th y cubed z to the 4th. I'm going to simplify this part and write it without a radical symbol. Remember, taking a fifth root, all you do is divide 5 into the exponents and use that exponent. So since fifth root means 1/5 power, so the fifth root of x to the 40th, you're really multiplying that exponent by 1/5, or dividing 5 into 40. So when I take the fifth root of x to the 40th, I get x to the 8th, since 5 goes into 48 times. The fifth root of y to the 25th, 5 goes into 25 5 times, so it's going to be y to the 5th. The fifth root of z to the 5th, 5 goes into 5 1 time, so we just get z to the first power. We don't have to write that exponent. Times this radical here, which cannot be simplified. So don't forget to write the index again. Fifth root of 16 w to the 4th y cubed times z to the 4th. And there you have the answer in simplest form. You should be able to do that. Some mistakes I see, some students will say, oh, 16, square root of 16 is 4. And they'll put a 4 here. They'll take this out and put a 4. They're not taking a square root. It's a fifth root. That 16 stays underneath the radical symbol. Okay? Anyway, those are some examples of how to use that product property, that product rule, to simplify radicals. Okay, here's another example out of the book. This one doesn't involve radicals, but there was one like this that said simplify this. I'm just going to go over it since it's in the book. Simplify 4 minus the square root of 20. This is on page 636 if you're interested, over 2. Okay, we're going to simplify this rational expression. We have the square root of 20. We want to simplify it if we can. So we have 4 minus the square root of 20. Since it's a square root, the index is 2, even though it's not written. We're looking for any perfect square, the largest perfect square, that divides 20. 4 is a perfect square, and it divides 20, and it's the largest one that does so. So we're going to write the 20 as 4 times 5. So we have 4 minus the square root of 4 times 5 over 2. And also, again, I warn you, I see students do this. They divide 2 into that 4. Oh, and this becomes a 1, and they put a 2 there. That's incorrect. You know, this whole numerator is over 2. You got to divide each one of these by 2 if you're going to, you know, start dividing. Wait till you're done simplifying. You'll see what happens. I'll show you. And also, don't divide 2 into 20. This is not 20 here. This is the square root of 20. That's some irrational number. It's not 20. Okay, so let's simplify this radical. And we've just learned how to do that just a couple seconds ago. So we have 4 minus, and then we're going to write that square root of 4 times 5 as the square root of 4 times the square root of 5 using that property we talked about, all over 2. The square root of 4 is 2. So this becomes 4 minus, replacing the square root of 4 with 2. 2 times the square root of 5, all over 2. Then, again, don't just like divide these 2's out, or just divide that 2 into